Okay, let us discuss this next problem. So we make the diagram and then we'll discuss the problem. So you see, we make the diagram. It's morning time. Fresh, cold breeze is there. And the total environment is slightly cool. Sun is coming. Sun wants to come to filter a screen of my window. So it's coming inside the room, very slow light. But it's beautiful. Only some part of sun is making a patch on the window. Only a small patch. If I open, it can come, but I will not open because some cold is there. People are going on the road with the bike. So morning time, everybody is looking fresh. Everybody doing for the today preparation they are doing for today's day. Okay, I think you have made this diagram. So you see, there is a planet of mass m and radius r, and there is a mass m. This object basically thrown with velocity v naught. This distance is d. If I make a perpendicular from here to here, so this distance is d, and this distance is a small d. Now the question asks, what should be the velocity v naught? What should be the velocity v naught? What should be the value of v naught so that this object is just able to graze the planet and escape? So just able to graze the planet and escape. So what should be the value of v naught? So we have to find what is the v naught so that this object will graze this planet. This means just able to graze the planet. This means what? And escape. So if this planet goes, so there is attraction forces. And if nothing has happened, if it does not give any velocity, what will happen? This planet will go in this direction. This will be attracted by this planet. So this object will fall on the planet. But if you give some velocity, this will go in this direction, always attracted. So initially it will go in this direction, and then there is attraction, so this will try to change its path, and it will change and it will come something like this. And if this velocity becomes 0, then it will fall something. If the tangential velocity becomes 0, then it will fall on the planet. If tangential velocity does not becomes on the 0, then it will go something like this. Are you getting or not? So this is important point. So this object is coming, this will go something like this. If tangential velocity is still there, this will pass something like, so this will graze. So this will just touch somewhere on the planet. It will just touch and then go. So you have to use a idea like this. A distance is just coming somewhere here, and this is going here. So you apply the angular momentum conservation and energy conservation, you will get the answer. Let me show you the path of planet. Another hint I will give you. So this will move in something like this. So this v naught, initial velocity is v naught. This distance is d, a small d. So this is going this way. Now this goes this way, and this makes something of this kind of path. Now this makes something of this kind of path. Somewhere it will come the nearest distance. So this point is the nearest distance. This the r is nearest, so r is minimum. So if r is minimum, this means at this point it will also have a tangential velocity v. So if this velocity goes 0, then it will fall. At the shortest point, if this velocity exists, it will not fall, it will graze. It will again escape. So even at the shortest distance v is not 0, that is when r is minimum, this v is not 0, so it will graze. Are you getting or not? So now you apply the angular momentum conservation and energy conservation. Things are easy. You will get the answer. So make a pause on your computer. Okay, now let us discuss the solution. Some of you might have done some work. I don't say that all of you have done. I assume that some of you must have done, and at least those who are interested in JEE have to do. Otherwise there is no point. So these problems you have to do your own. Now if I see there are only central forces acting, that is the gravitational force acting between these two masses, So I can say angular momentum of system remains conserved because this force is passing through this. So I can say angular momentum about this point. So let us say angular momentum about point A remains conserved. So angular momentum conservation about A. Are you getting not? About A there is no force. Now initial angular momentum. So V naught is this. MBR, perpendicular distance from this to velocity vector, this is D. You getting or not? And this makes an angle 90 degrees, so this becomes MB not D. When this is here, again this is the velocity is perpendicular to the radius vector because this is the minimum. So angular momentum becomes MBR. So this is my angular momentum about point A. Now energy conservation is easy. You see, here I have energy half mv naught square, and potential energy is minus gmm by R. So this distance is R. So this distance is R. So this distance is capital D, this distance is a small d. So this becomes capital D whole square plus a small d whole square under root. So this potential energy is gmm by capital D whole square plus small d whole square. Now at this point velocity is v, so half mv square minus gmm by this distance r. So this is the potential energy. Now this is the total energy. Now we have energy conservation. Now we can solve. We have two equation and two unknown. V is unknown, so I have to solve for V, and R is also unknown. So you solve using these two equation. So V is unknown and V naught is also unknown. So you have three unknown. V is unknown, V naught is unknown, and a small r is also unknown. So these three things are unknown, and basically problem say this just grazes. So I can solve for, so this just grazes, this means just touches the planet and then goes. So I can assume capital R is equals to a small r. So this distance just grazes, so this distance is r. So this comes here and just touches and then goes. So I can say capital R is equals to a small r is equals to capital R. So if I take a small r is equals to capital R and then I solve, I can get the answer. So you see, so from equation 1 I can write V is nothing but mm cancels out, so V is nothing but V naught d by r. So V naught d by a small r, and a small r is equals to capital R. So I can write V is V naught d by r. Now energy conservation, if I put a small r, if I replace a small by capital R, this becomes gmm by capital R, and this velocity, if I put this value V naught d by capital R whole square, so this is the term I am getting. Now I have, if I cancel m, so this becomes something like this. If I cancel m, now if I take V naught one side, so this is the V naught, this is the V naught term. If I take V naught term this side, 2gm term this side, and if I solve, I will get this. And this is your task. You can always solve. Are you getting or not? So if you solve, so you see this problem even also we have applied two things, energy conservation and angular momentum conservation. You will get the desired result. So you have to simply plug the values of, so you see, plug the values of V naught from equation 1 to equation 2, and you have to a small r is equals to capital R. Are you getting or not? Okay, so let us make a pause and then you note it down. We'll discuss the next problem. I am making videos in a small so that the size becomes slightly smaller. So I am not elaborating, I am not giving you too much time to write. You just make a pause because you can always make. It's your computer. You can always handle. So you can always make a pause on your computer and you can write. So that's why I am making these videos slightly shorter and shorter so that the size of the video becomes shorter. Okay, we'll discuss the next problem.